Okay, we'll get started in just a second. Okay, so let's get started. So we are going to continue the discussion on World Wide Web from last time. So today we have three topics to cover. There's web caching, which I'm going to start with. Then there is content distribution networks and edge computing. Okay, they are all related, as you will see. Each one will build on the previous things we talk about. So let's start with web caching. So this two figures should already be familiar to you. We've seen it several times. The top figure here shows you a typical client server system as it exists in the web. So your web browser that's talking to a web server. And then we said you can turn this into a client proxy server system where there's a proxy server sitting between the browser and the web server. Okay. In this case, it's a web proxy. And specifically today, we are going to look at how do you design this web proxy when its main functionality is caching. Okay? So this proxy is going to cache web pages and images that you get from web servers. So your browser is first going to contact the web proxy, okay, with some URL. If that URL is cached at the web proxy, you're going to get those contents immediately. You don't have to go to the server, and then you're done. And if not, you have a cache miss. That's going to require the cache to contact the server, fetch the content, put it in the cache, and then hand it back to the browser. Okay, so that's the picture you should have in mind. This is a slightly more complicated version of web proxy caching that we are also going to discuss today. Okay, so this version of web proxy caching involves multiple caches, and in this figure, you will see that there are three proxies. Okay, each of them has a cache. Okay. The principle is the same. Okay, you might have a client, as you see here, it contacts the web proxy, okay, with a HTTP request. If that cache at that proxy already has the content, you just return it to the proxy, you're done. Now, if the cache at that proxy does not have the requested URL, okay, in the previous case, in the simple case, you are just going to go to the web server. That's a cache miss. You go to the web server and get the contents. But in this case, because there are other proxies nearby, you can actually ask those proxies if they have the content before you go to the server. Okay? And the idea is if there are other nearby proxies, maybe you can fetch the content faster than having to go to the web server. Okay? Now, if you have this model where there are multiple proxies that are collectively working together to serve client requests, you get what is called cooperative caching. Okay? Typically, caches are standalone. Okay? This previous picture showed you a single cache. So the browsers or clients connect to that cache, and the cache can either return the content, talk to servers. Okay? But if you have more than one and they are actually working together, okay, as I just showed you here, you get cooperative caching. So we are going to look at both of these aspects today. Okay? We'll start with single level cache, and then we'll generalize that to multiple caches. Okay? But the more important thing we will discuss first is consistency. If you remember, when I talked about replication, I said when there are multiple copies of any data item in a distributed system, you need to ensure that all of these copies are consistent with one another. Okay? The same is true of a web cache. Okay? You can think of a cached web page as being a replica of the original web page at a web server. Okay? Now, let's assume it's a cached version of some news website page. Okay, let's say CNN as an example. So you have the CNN front page that's in the cache. Now, if the front page on the origin server is going to get updated, okay, then the content in the cache have become stale. They're out of date because the copy on the server has changed. Okay? Now, somehow you need to make sure that whenever there are updates at the server, the cache actually does not serve stale content, because maybe another browser sends a request saying it wants to get the home page of CNN, okay? And then the cache might say it's already in the cache and return a stale version. And that's not good, because now the user is seeing an out-of-date version of the web page. So you want to ensure that whatever contents are kept in the cache are always kept consistent. Yeah, so that's why you need to deal with consistency. We talked about consistency models a few lectures back. Here we are going to look at some simple consistency techniques that try to use some of those ideas and implement them in a web caching framework. Okay, so I think the thing you want to keep in mind as we design some of these consistency techniques is that web pages are actually going to be very different in terms of how frequently they are updated and how frequently they are actually accessed. So let's say that there are some, I'm going to use the term object to mean either an HTML page or images or anything else that's embedded in the page. So you'll say some objects are static, which means once they are created, they are never going to change. Okay? So those are called static objects. And many other web pages tend to be dynamic. They change frequently. Okay? News websites are a good example. They are going to be, maybe there is a breaking news section in that news website that gets updated frequently every few minutes. So the page actually changes every few minutes. Okay? And then there may be other pages that change every few days, or maybe once you create, you don't change it at all. So the update frequency is going to vary, okay, from a few minutes to a few weeks to never. Okay? Now, the access frequency might also vary. Access frequency means the popularity of that web page. How many users are accessing that web page per unit time every second. Okay? There are some pages are very popular, right? Popular news sites, e-commerce sites, they're all extremely popular. They get millions of users accessing them every day. And then you might have less access pages that may be personal websites or other pages that don't get very much access. So that's called the popularity of the page. That also varies significantly. Okay? And we need to keep both of these issues in mind as we design consistency techniques. Okay? So we will look at a few, but by and large, how is a proxy cache going to maintain consistency of an object, okay, which could be a web page or an image. Okay? So suppose that this object has changed on the server. Okay? Somehow the cache has to be told that the object has changed, so that if that object is cached, it's invalidated from the cache. Okay? So the way you can do this is a simple thing is the server can then send a notification to the cache saying the object has changed. Okay? That could be an invalidate message saying if the object is cached, discard it from the cache. So then the cache can then just remove it so that you don't store stale content. Okay? Or the server can actually send the new version. Rather than saying invalidate, you can just send the new version of the page, and then the old version in the cache gets replaced with the new version. So in this case also things are fine. Okay? So either you can send an invalidate or you can send an update. Is this clear? Okay. Now there are two ways you can do this, which is either you can use a push-based technique to do either of those two things, or you can use a pull-based technique, and we'll look at both and try to compare them a little bit. Okay. Let's start with the server push approach. Okay. As the name server push indicates, okay, it is the responsibility of the server to push invalidation or update messages to the proxy cache or every proxy cache that caches content whenever something changes at the server. Okay. If the server observes that a web page has been updated, its responsibility is to push an invalidate message or an update message to every proxy cache that has it. Okay. So the server has to keep track of all the proxies that have requested content from it. It has to have a list. Okay. And whenever a web page changes, it can look at the list of which proxies have cached that specific URL, and then it has to send a notification. It has to notify the proxy. Okay. The notification could be one of two types: an invalidate message that's going from the server to the proxy, or an update message. Invalidate simply means this URL has changed, invalidate it from the cache, which means remove it from the cache. So then the stale contents are removed. Okay. Update means you actually send the full new version of that object, and then the old version in the cache gets replaced with the new version. Okay. So one question you can ask is, suppose that a web page has changed. Okay. The server has one of two choices to notify all the proxies. Okay. Which one should it pick? Should it send an invalidate message or an update message? And under what scenario would you send one over the other? Any thoughts on this? The question clear? Okay, the server has to note the web page has changed at the server, so it's now the server's responsibility to notify the proxy. In this case, there's only one proxy shown for simplicity, but there could be more than one. Okay, that's to notify the proxy. Okay, you can do this through an invalidate message or an update. So when would you send one or the other? Yes. Yes, so that's good observation. The first question is you should ask what is the overhead of these two techniques. Okay, an invalidate message is going to be a short message. It's going to just have an invalidate with the URL and you just send that. Right, so that's a fairly short message in terms of overhead. An update actually includes the entire page, or it could be an image which could be large in size. So the overhead or the size of an update message is going to be larger than the size of an invalidate message. Okay, so you have to make, if you're going to send a larger message, you want to make sure that the extra cost of sending a longer message is going to be worth the that you have to make sure that you want to pay that extra cost in terms of the benefits you're going to get. Okay? So as was just pointed out, you will send an update if the web page is popular at the proxy. There are lots of users requesting that content at the proxy. Then the server can pay that extra price and say, here is the new version. Okay? And then you send that, the object gets replaced, and then the next request that comes to the proxy automatically gets the new version of the page. Okay? On the other hand, if the URL that has changed is not very popular, it's infrequently accessed by the user, there is no reason you want to send an update, because what if nobody accesses it afterwards? You paid all this extra cost of sending this page, but nobody accesses it because it's not very popular, it's infrequently accessed. So in that case, you're better off just sending an invalidate so that the object is removed from the cache, there's no stale version. Okay? And then if somebody accesses that page subsequently, okay, it's going to be a cache miss and the proxy is going to request it anyway. Is that clear? Okay. So whether you pay that extra cost of an update is going to depend on the access frequency of the object or the popularity of the object. Okay. So that's what's mentioned here. Send updates for more frequently accessed objects, invalidate for the rest. Yes. Okay, question is, can both of them be used in the same system? Yes, there is no reason to just have one or the other. The server can have both of those options, and it can decide for certain URLs it uses updates, for others use invalid. Okay. Yeah, so question is, does it mark popular pages? How is that going to work? So in this approach, if you are going to dynamically decide between updates and invalidates, you need extra information. The server needs to know the popularity of web pages at various proxies. So it needs to know what's the access frequency, and keep in mind the access frequency may not be static. Okay, you might have, let's say, a breaking news item on a news website. There are lots of accesses to that because everyone is trying to read the news, but maybe 2 days later, you are not going to get access to that page, something else gets popular. So the popularity of any page is not going to be static over time. It will itself vary, but whatever it is for the current point in time, the server needs to keep track of it so it can decide between one or the other, and it needs to keep updating the popularity, because if there's a big change, it might switch from one or to the other. Okay, so those are all things you have to do, but so that brings us to some advantages and disadvantages of server push based approaches. So the first thing to keep in mind in server push is it gives tight consistency guarantees, because as soon as a web page changes, you are sending out messages to the proxy. Proxies will then make the appropriate decision of either discarding stale content or replacing it with the new version. So you are going to get reasonably good consistency guarantees. I would not call this strong consistency, because there's always a delay between the time a web page changes to the time that message actually arrives at the proxy. So that small amount of delay means you cannot really call this strong consistency, which is what we had studied when we are talking about consistency models. But it is tight. It's reasonably close to strong, but not exactly strong consistency. Okay, that's the first advantage. The second advantage is, in this case, proxies can be passive. Okay, they are just caches. The server is doing all the work of deciding how to implement consistency. Okay, because the server's job to notify the proxy, proxies are not doing it. Disadvantages, there are several. First is the server has to keep state. Okay, the state in this case is the list of all the proxies that have cached content from it. Okay, because once a proxy requests a web page and keeps it in the cache until that web page is discarded from the cache, the server has to keep track of that proxy, and every time that web page changes, it has to send it either notifications or updates, that state information. Okay, so this has made the server stateful. Okay, HTTP by itself is a stateless protocol. There's no state, but if you add consistency overheads or to the at the server on top of just HTTP, you are making the server stateful. Okay, so this amount of state could be large. For popular pages, there may be thousands of proxies that have requested, tens of thousands of proxies that may have requested a page. Every time it changes, you have to keep track of all of the proxy IP addresses, the URL, and then send them notification. So you can have a substantial amount of state that you would have to keep at the server in this case. Okay, so it's a stateful technique. Okay, and second issue is the state might have to be kept indefinitely. If the proxy decides to cache an object for a long period of time, the server is responsible for sending invalidate or update messages for that long period of time, and that could be a very long period which can trend to infinity. So you might have to keep this state for a long time. Okay, once the proxy decides to replace or discard that content, then the server can stop sending notification. But until then, you have to send notification. Okay, so there is this issue where the server becomes stateful and the state has to be kept for longer period, which also means that if the state is kept in the memory of the server, not on disk, and the server crashes, all of the state disappears. Right? So you have to make either you keep it on disk, in which case you can survive reboots, or if you keep it in RAM, then if you reboot the server, all of this information is gone. So now you're not giving any consistency guarantee because you don't know which proxy is caching what page. Yes. Yes.
So how the server?
Okay. Well, so that's a good question. So question is, the cache size might be limited. It's not infinite at every proxy. It may be limited by the size of the disk. So if your cache replacement, right, which means that new items are brought in, old items are removed. I think all of you are implementing cache replacement in lab 3, right? You're using least recently used LRU as your cache replacement technique. So a web proxy will also implement some sort of a cache replacement. Another question is, how is the server to know that contents have been removed? Okay, we didn't actually talk about that, but if the proxy could notify a server saying that an item is removed from the cache, as one example, right? Otherwise, the server will not know what is actually stored at the proxy, whether it's been removed or not. Okay, but that's an additional overhead that the server has to get this information from the proxy. If it otherwise, it will send wasteful messages. Okay, yes.
From understanding the validation, the assignment. So whenever there's nothing, just delete that updated thing.
Yes. So I think that you're asking about the lab, right? No, not web prop. Yes. So from the lab perspective, you're implementing something very straightforward. Whenever something changes, you just invalidate. You don't have to send an update. You just invalidate it from the cache. Okay, so that's much simpler than actually sending a more recent version. Okay. Yes. All right. So now let's talk about the other approach, which is pull-based. Okay. So in this case, everything is flipped. Okay. So in a pull-based approach, it's the responsibility of the proxy to maintain cache consistency. Okay. So essentially what the proxy is going to do is, for every cached page, okay, it's going to periodically poll the server. Has this page changed? Okay. If the server says, yes, it has changed, then you invalidate it. You remove it from your cache because now you have stale version of the page. Okay. But if the server says, no, it hasn't changed, then you can keep it around. You know that the web page is still current. Whatever your cached is the same as what's at the server. So this is called a polling based technique. Okay, so you can poll the server to keep checking whether the web page has changed or not. And interestingly enough, you can do this with standard HTTP messages with no extra protocol needed. Okay, the way you do this with HTTP is HTTP has a, as you all know, HTTP has a get method, which is what you use to get a web page. You say get and have a URL, and then you fetch the page. Okay, now it turns out that HTTP supports what's called a conditional get. So you can specify a condition, and the get will work only if the condition is true. If the condition is false, the get will return null. Okay, so the type of condition you are going to actually specify is what you call, it's called an if modified since, and you specify a date, right? So you can basically, the proxy can say, I fetched this page yesterday at noon. Okay, so now when you poll the server, you say HTTP get if modified since yesterday noon. So you specify a date saying, if it has been modified since this date, I fetched the page, then send me the new version. Otherwise, if it doesn't change, you return a null. Right? So that's called a conditional get. That's supported by HTTP. This is called IMS, if modified since, then IMS get. Okay? So you can simply use an IMS HTTP message to keep polling. It's a type of a poll. It says, tell me if it has changed. Okay, if it has changed, you are also asking for the new version of the page clearly. Okay, and if it doesn't change, then you just get a null, so you know that whatever is in the cache is current. Okay, so you can implement a pull-based approach using simple HTTP. Server push approaches, of course, you don't use HTTP, except now with the newest version, HTTP supports push. Okay, HTTP has always been a request response protocol, but the newest version supports push. So with that, you can actually do server push, but anything that's older, you don't have HTTP as your push-based protocol. You have to implement some other one. Okay? But pull-based has always been possible using HTTP. Okay? Now that brings us to this next question saying, how frequently should the proxy check with the server? Okay, I said you poll the server periodically, and then the server will tell you if the page has changed or not. So that's good. But then how frequently would you do it? Okay, should you do it every minute, every hour, every 6 hours? Right? So you can pick your polling frequency, right? And depending on what you pick, you may get different results. Right? So let's take an example. Let's say, go back to this example of the front page of CNN or New York Times. Right? So it's a page that gets updated frequently. At least it has some breaking news section and so on. So that it will get updated every few minutes. Okay? Now, if the proxy decides to poll every 6 hours, okay, you fetch the page, and then you poll after 6 hours, what's going to happen? Is the question clear? You fetch the web page, you put it in the cache. Okay? Your polling frequency is set to 6 hours, which means you poll every 6 hours, but the web page is changing every few minutes at the server. What does this mean? Sorry? You will serve outdated content, right? You will fetch the page, few minutes later it will change, but the proxy is not checking with the server anytime soon. It's going to check after 6 hours, right? So for the next 6 hours, all requests to this proxy for that page will return an old version of the page. Okay, the users will see stale content. Okay, so that's fine. So we'll say, okay, that's not a good idea. You should not poll every several hours. Let's start polling every minute or every second. Okay, so every minute or every few seconds, you are going to send an HTTP request to the server. Okay, and if you have a page that's changing frequently, that's good, because every few requests, maybe you get a message from the server saying, yes, the page has changed since the last time you fetched the page, and here's the new version. So in that case, you will get the newest version of the page in your proxy. Okay? But now, if you use this strategy and you're trying to poll a page, that doesn't change very frequently. Right? Let's take our class web page. Right? I update it twice a week with the lecture note. Right? So it's being updated once every few days. If you check with the server every second saying, has it changed? It's just going to keep saying, no, it has not changed. So you're wasting a lot of requests asking the server, has it changed? Has it changed? And the server says, no, it has not changed. So you spent a huge amount of overhead in terms of messages just to check when the request always returns a null. Right? So that's not very useful from a efficiency standpoint. Right? So what does this tell us in terms of polling? What should the proxy do? Can you speak up a little? What did you say? Okay. So the best approach is to somehow know how frequently the web page might be changing at the server and match your polling frequency to the update frequency. Right? For frequently changing pages, poll more frequently. For less frequently changing pages, poll less frequently. That's a good strategy because then you're matching your update frequency, not update, polling frequency to the update frequency. Okay? But that's easier said than done, because how is the proxy to know how frequently the web page is going to change at the server? Okay? Yes. Yes. You have to come up. You will come up with an adaptive technique. We'll get to that in just a second. But you're right. But normally a proxy is not going to know, right, how frequently a web page will change. What does it know? It just knows some HTML page with a URL. So somehow it has to discover the update frequency. Right? So that's an additional overhead on the proxy. But let's try to figure out how to do this. Right? So exactly what was said here. Here's an adaptive approach. Right? So what you're going to do is you will start with a conservative update frequency. So the first time you fetch a page, you know nothing about the page. So you will say, let's poll every second. Okay? So you poll the server. Maybe if let's assume for this example, this page is not very frequently updated once a day, just as an example. Right? So the first time you ask the server says, no, it hasn't changed. So then rather than asking again a second later, you reduce the frequency. You say, I'm going to now ask every 10 seconds. Okay? So 10 seconds later, you ask. The server again send the IMS request. It says it hasn't changed. So then you increase it further. Okay? And so you do this until you hit a time and the server says it has actually changed. So now you discovered when you fetched the page originally, when it changed next. So you have some notion of, okay, an update has occurred after so much time that has elapsed since the page was fetched. Okay? So it tells you something about how frequently the page is changing. So you can then use that frequency to actually poll. Okay? But there is no guarantee that the update frequency is static either. Okay? Think about maybe you have a blog, right? So you can update your blog anytime you want. Right? That doesn't mean if you updated it now, you are going to wait 2 days to update it. You can update it after a few hours, few days. So the update frequency is not going to be static. It can change. Okay? So the polling frequency also has to actually be adaptive. So essentially, if you find that an object has been updated between 2 polls, you actually reduce the polling frequency just in case it has changed. So that was that exponential back of suggestion that was made. So you can decrease exponentially, you can decrease linearly, whatever it is, you got to decrease it. Okay? And then if between 2 successive polls, there has been no update, you can increase the frequency a little bit, otherwise you decrease it. So this way you can keep adapting the polling frequency to whatever the update frequency is. And if it keeps changing, you keep changing the polling frequency as well. Okay? So this is an adaptive approach which does not assume any prior knowledge of the object update characteristics. The write frequency can change and the polling frequency will keep tracking it. Is that clear? Okay. So that's our polling based approach. So that brings us to advantages and disadvantages here. So simpler technique than push, you can use if modified since conditional get request, so everything can be implemented using HTTP. The server is now stateless. All the work is being done by the proxy. The proxy is the one polling. The server just has to respond. There is no state at the server, unlike the push-based approach. So this is going to be resilient to both proxy and server failures, because the server fails, then there's no impact on the polling frequency. If the proxy changes, you can just restart your adaptive interval from a small value and keep increasing it. So no harm done, maybe a few more messages get sent. Okay? So those are the advantages. Disadvantages of the approach is that the consistency guarantee is going to be weaker than server push. The server pushed approach always assumes that as soon as a page has been updated, the server will send notifications to all the proxies. So the proxies know shortly after a page changes that the that you have to invalidate it from the cache. In this case, you have to wait for the next poll, whatever that is. Right? So there's going to be a period between the time a web page has changed at the server to the next poll, and in that period, you're going to be having stale content in your cache. So any request will see stale content. So it's weaker guarantees than what server push will provide you. Okay. Now you need more intelligence at the proxy to decide the polling frequency, adapt it, and so on. So this has to have more overhead at the proxy. The message overhead is also higher than server push, right? So if you think about the message complexity of the protocol, in server push, for every update, there is one message that goes to the proxy. That's a notification or so whenever it changes, there's a web page that changes at the server, you send one message. It's either a notifier or an update. Okay. In the polling case, there may be many round-trip messages where you are doing conditional gets before the page actually changes, because you might use a more conservative frequency, for example. Right. So there is going to be higher message overhead than the server push approach. Is that clear? Any questions here? Yes.
Practice those website.
Okay. Question is, in practice, do websites maintain their own proxies? Are proxies generic? So I will answer it two ways. So the way in the old days, right, you could just download a web proxy. Okay, it was open source, and you could deploy your own web proxy, and it would do something like this. Right? The websites had no control over the proxies. They never actually did server push. Proxies had to actually use pull-based, because servers had no control over anything users were doing. You could deploy a proxy. For example, the CS department can deploy a proxy, and anyone who's accessing web content actually goes through the proxy. So maybe cached content is delivered to them faster. That's how things used to work. Okay? That's not how things work anymore. It's actually the servers are now using a third-party system called a content delivery network, which we'll get to, that will actually use caching to accelerate content. Okay? So it has actually now moved from the users deploy this to get content faster to servers that have lots of content to deliver actually use a caching-based system, usually a third-party caching-based system, to deliver content. Right? So we'll see both of these. So this is something we've already seen. The CDN we'll get to in just a few slides. Yes.
So we talked about how there were different messages.
Yes. Are you asking about the push-based approach?
Yeah, and with the push base, we have two different messages.
Yes. Okay, that's a good question. So question is, in the pull-based approach, do we have one type, like in the push-based, you had a notify message that could be an invalidate or an update. Okay. Question is, in a push-based, do we have only one or two? Right. So it turns out that it's actually combined, because you are always using a conditional get. Okay. So the conditional get is serving both as a notify and an update. If the content has not changed, the conditional get returns a null, which essentially is like a notify saying nothing has changed. But if the object has changed, the conditional get, the condition will be true, and then you will fetch the content, because it's a get request after all. So at that point, it becomes an update. So it's basically both of these are at play, and depending on whether the condition is false or true, you will get if the equivalent to a notify or of an invalidate versus an update, if that makes sense. Is that clear? Any other questions here? Okay. So we will now look at a different approach, which is trying to combine both server push and client pull into a single approach. Okay, we saw that these were, it's not client, but proxy pull and server push into one approach. Okay. This brings us to a concept called leases, which we have not encountered yet. Okay, this is the first time we are hearing this term. This concept of leases is a more general concept in distributed system. Today, we are going to look at this lease concept in the context of web proxy caching. Okay? But let me explain what a lease is first, and then we'll see how are we going to use it for proxy caching. Okay? So what a lease means is it's like a lease that you might sign to rent an apartment. Right? So what is a lease? A lease is effectively a contract. Okay? It's a contract between two parties where you agree to something and you get something in return, right? So maybe in an apartment case, you are basically agreeing to use the apartment and you are going to pay a rent for that period. And there's a duration for the lease which says it's valid for a certain amount of time. Okay? In distributed system, it's a similar concept where a lease is a contract between two entities in a distributed system for a period of time, and the two entities agree to something. Okay? In our case, okay, because we are talking about web proxy caching, what we are agreeing to is the server will agree to notify the proxy of any updates to a page. Okay? So the lease says this for this duration of time, the server agrees to send notifications whenever the page is changed. Okay? So you can get a lease for 1 hour, and then the server is obligated for that 1 hour to send any notifications whenever that page changes. A lease can be gotten on a per URL basis. Okay? So how are we going to use it for web proxy caching? So here's a picture that's going to show you what actually happens. So here's a client, the browser is going to send, it says read, but it's really sending an HTTP message which comes to the proxy. Okay? Let's assume this is the first time the proxy gets a request for this URL. So its cache does not have that page, right? So it's a cache miss, right? What is it going to do? Normally, it would just go to the server, get the content, put it in the cache, and return that content, right? But in this case, we will send a GET request, but we'll also send a lease request. Okay? So we'll say, I want this page, but also I need a lease on this page. The server is then going to send a reply, but then it will actually specify you have a lease for a certain duration. Okay? The server gets to pick that duration. Okay? So now the proxy can cache the content, and so long as the lease is active, it is guaranteed that the server will send it notification. So it knows that so long as the lease is active, its contents are going to be fresh. You will not have stale content because the server needs to notify. Okay? Once the lease expires, the proxy can do one of two things. It can just discard the page from its cache, saying the lease has expired, so it's no longer safe to keep the page in the cache. So you can just throw the page out. Okay? Or you can renew the lease. You can send a request saying, I need another lease on the object. And then the server will give another lease for a certain duration. And then you know that it's fine to keep the page because it's going to be fresh. Is that clear? So what a lease means in this case? So lease is basically, in this case, a contract between the server and the proxy where the server agrees to send notification or push notifications while the lease is active. And once the lease is expired, the server can stop sending notifications to the proxy unless it gets renewed. Okay? So now let's ask, what does this do for us? How is this, first of all, hybrid approach? What does it give us in terms of what the properties were for server push and pull and so on? Okay? So first thing is, depending on the duration of the lease, you can get different properties. Okay? So let's say the server, just for example, right, server gives an infinite duration lease. A lease duration is infinite, it never expires. What does this technique do? Okay, the server is now going to send messages, notifications forever. So what this lease-based technique has essentially become a server push approach. Right? Because in server push, there was no lease. The server was obligated to keep sending kind of invalidates or updates indefinitely until the proxy effectively told it to stop because it threw out the page or something like that. So if you give infinite duration leases, it's become server pull. If the lease duration is 0, okay, this is the same as client pull, because what will happen is you will get the content, okay, and then the lease will immediately expire. So then the proxy really has to go and ask for that content again with a new lease, which is like polling. Right? So every time a request comes, it doesn't know if the page is valid or not. It is actually going to poll on demand. A request comes in, you ask the server, maybe you send an IMS request, okay, and the server says the page has changed or not, depending on one or the other. You'll fetch the new page, put it in the cache and respond. If it doesn't change, you will just respond with whatever you cached. Okay, so zero duration leases, this becomes analogous to proxy pull. The infinite duration lease, it becomes the same as server push. If you have something in between, it is a mix of the two. Is that clear, what I just said? Okay. All right. So now that brings us to the question of how does the server know what lease duration to pick? This is somewhat similar to asking how do you decide the polling frequency for a pull-based approach. Okay, so what can we do? How should the server decide for a page how much duration leaves to give it? Can we do something like what we did in the pull-based approach? Tie it to something that we know about the web page? Yes. Yes, so you can ask, depending on how frequently you are asking for lease renewals, depending on how frequently the page is getting accessed at the proxy, depending on how frequently the page is getting updated at the server. You can use any of these techniques, not techniques, metrics to decide how long or short the lease should be, right? If it's a popular page at the proxy, just as an example, okay, the server can give a longer lease because that page is being frequently accessed. So it's in the server's interest to make sure that the proxy is responding with the current version of the page, not sending stale content. So you can have a longer lease that allows the server to send notifications for a longer period of time. Okay? But if the page is not popular, then there is no reason to have a long lease. The lease can expire, and then let the proxy ask for a new lease later on when somebody else accesses that page. Okay? So you can tie the lease duration to the popularity of the page, which means the number of HTTP requests that are coming in for that web page. Okay? You can tie it also to how frequently the web page is changing at the server, because the update frequency is directly connected to how many messages the server needs to send, right? So maybe for popular pages, you might say that's a lot of overhead. I can reduce the lease duration if the load on the server is high for some reason. So that will allow you to not increase its load further, because then it has to send lots of messages every time a web page is. So you can tie it to the load on the server and the update frequency as another example. So there are many approaches you can use. Okay, so I mentioned age-based leases, which say depending on how old the page is, if the page has not changed frequently, you can tie it to the age of the page. You can make it connected to the renewal frequency of the page. How frequently is the proxy asking for it, which is tied to the update to the read frequency. You can tie it to the load on the server. Okay, the load is high, then you can make the leases shorter. Okay, so all kinds of techniques can be used, but regardless of which technique you use, you come up with a lease duration, you hand the proxy a lease, and then so long as the lease is active, you have to send notification from the server's perspective. Okay. Is that clear? Okay. So one thing this does is it gets over some of the disadvantages of the server push approach, because now the amount of state the server has to maintain can be controlled by controlling the lease duration. Okay? If the state is growing significantly, you can start giving shorter leases so that they expire. Once the lease expires, you can throw away information about the proxies. The state space can be reduced. Okay? Or vice versa. If you are not keeping a lot of state at the server, you can afford to give longer leases so you can keep some more information around. So in the server push approach, you had no control over the amount of state that was maintained. Right? Here you can use the lease duration to control it. So you can get over some of what we talked about, the disadvantages of the push-based approach. Okay? Yes. Right. If a page is popular, typically, which is called the renewal frequency based or popularity based, it is better for the server to give longer leases. That way, you are not making the proxy do extra work of renewing the lease. You can keep a longer lease and keep sending notification. That's the better approach. Yes. Yes. Regardless of which policy you use, the server and in some case the proxy have to track some metrics and use that metric to decide. That is true. Right? Because without knowing that, you cannot adapt or change the lease frequency on a per URL basis. Then you can statically configure the lease duration and then not have to do any of this, but that can waste messages. Right? So this is adapting it to some characteristic of the workload. Okay, so that's lease based, and we will now switch gears and talk about cooperative caching, and then we'll get to content distribution networks. So we are going to now go from a single proxy to many proxies. Okay? So assume now you have a distributed system where there are many proxies deployed, maybe by a single organization, maybe different organizations, but these proxies have the ability to cooperate with one another. They can talk to one another and they can collaborate with one another to serve user content. Okay? The question is, what does this give us and how does it help? Right? So here is an example of one approach. This is called hierarchical proxy caching because the caches are arranged in a hierarchy. It's a single level hierarchy where there is a parent cache, which is the root of the tree, and 3 leaf caches. So it's a one level tree with 4 caches total. Okay? You can have arbitrary levels of nesting in a hierarchical caching approach, but this is just showing you a very simple approach. And you will see at the top is your web server, at the bottom are client, the blue things are client, which are browser, and in the middle is your web proxy system. Okay? It's a proxy system with 4 caches. So let's now ask what is going to happen. So here is an example where this client here send a read request. Read means you ask for made an HTTP request, a GET request. Okay? So it goes to that proxy. Okay? That proxy is going to check if the web page A is actually cached or not. Okay? Let's assume it's not cached. It's a cache miss. Okay? Now, if that was a single proxy, a cache miss means you have to actually go to the server, get the web page using a standard HTTP request, and then put it in the cache and respond to the user browser with that page. Okay? But this is a cooperative caching system. So rather than immediately going to the server, this proxy is going to ask its neighboring proxies whether they have the page. Okay? So here is what they will. You will see that these red arrows are actually sending a request to 2 nearby leaf proxy as well as the immediate parent. That red arrow is labeled ICP. That ICP stands for Internet Cache Protocol. This was a protocol that was developed for caches to talk to one another and request content. So you are essentially sending requests to your peer caches and one level, the parent of this peers, saying, is the page available? Right? So if any of them have the page, they will respond to the cache with the page, and then you're done. You'll send back a response to the user. Okay? And the idea here is these caches are closer to the requesting cache than the server. Okay? The caches are further away, then you did not gain anything from this. So it will take you longer to get it from a far off cache than it gets than going to the server. But if there are caches nearby, maybe they can communicate faster and you can fetch the content faster. That's the reason you're trying to do cooperative caching. But we'll assume in this case that the web page is not cached anywhere. Okay, so none of these caches have it. So this is called a global miss. You don't have it locally. That's a local miss. The proxy asks other proxies, they don't have it either. So that's a global miss. Right? So you get these green arrows back saying it's not available. So then you actually forward, okay, the request to the parent saying, go get this page. If this was a multi-level hierarchy, the same thing would repeat. This parent would ask its leaves, it would ask its parent, and this request will propagate up the tree. But we are already at the root in this case. Okay? So because the parent has already said it doesn't have it, it's going to send a HTTP request to the server. The server will send the response back to the parent. The parent will send it back to the cache. The cache will send it back to the browser. Okay? Is that clear? What's actually happening? Okay, so that basically is how you are going to handle misses. Hits are fairly straightforward. If you have a local hit, you basically ask the cache is going to return the result and you're done. Or if you don't have it, you ask the neighboring caches, they return the result and you're done. Okay? The problem is when you don't have it, your request is percolating up the hierarchy until you fetch the content from someone who has it or the server. What is the advantage of hierarchy? Here you actually have multiple caches, right? So there are serving other users. So arrange them in a hierarchy so that you can cooperate and try to fetch the content from one another. So effectively, this 4 caches are acting as a union of one big, think of this as one big logical cache, which is constructed from 4 small physical caches, right? So when you make a request, you think about, does this logical cache have the content somewhere in the system? If so, you track it down and you fetch it from it. So you don't need to have that content at your local cache, but if it's somewhere in your overall system, it's there in your logical cache, you can get it. That's the idea of cooperative cache. Okay. Okay, question is, what is the benefit of the layer? Why are you doing this? So this is a very simple 4-node system where maybe you could have just asked all the nodes. There was no need for hierarchy, but assume that you have thousands of these, right, that are cooperating. You don't want one cache to ask 1,000 other caches saying, do you have this content or not? You want to somehow limit the range of what you're asking to nearby caches. So the hierarchy can allow you to localize your request to only those caches that are near you, rather than asking some cache that's very far away. A, that's going to be very slow. You might have as well gone to the server, and B, is wasting a lot of messages. So you can limit the overhead and try to get it faster if possible. That's the basic idea. The question is the parent going to ask, is it much further? So each node is asking its nearby caches. Not necessary that those nearby caches are actually close to the leaf. That's all it is. Okay? But having said that, what is one disadvantage you can see from this example that I just showed you? Okay? If there's a cache miss, and specifically a global cache miss, it's going to take a long time. Here's a user, right? They are just asking for a web page. And you can see how many messages have been exchanged just to get that web page. It would have been much better in this case for that user to forget about caches, just go to the server and fetch the web page. It would have come much faster than all of this extra work that has happened just to see if the web page is even present at any cache and to fetch it, right? So what this is saying is that global misses are actually very slow and expensive. Expensive in terms of the messages that are exchanged, and slow because you're asking, there are maybe multiple levels, your request is percolating up, and you're trying to see, is this web page anywhere in the system of these caches? Okay? Eventually the answer is no. That's when you go to the server. Okay? So hits are good because if you have a local hit or you have to get it from another nearby cache, that's still faster than going to the server. But misses are not good from a user's perspective. It takes a long time. The user is waiting for the web page and the page doesn't seem to load. That's not a good experience. You put the cache so that the page would load faster. You could get it from the cache instead of going to the server. Now, when you have a global miss, you actually give worse performance to the user than if there was no cache at all. Is that clear? Okay. So then there's a question, okay, if you want to have cooperative caching, but you want to get rid of some of this extra overhead, what can we do? Right? How can we actually get rid of this overhead? Is it clear what I'm asking? That you don't want global misses to slow you down, that you still want hits to actually speed things up. Okay. So you can say, I can send the request to the actual server and the parent. Okay. You could do that, but one of the reasons you put the cache in there in the first place is to also reduce the load on the server so that you can absorb some fraction of the requests that are going to the server are absorbed by the caches. So the server doesn't have to see them and the server load is lower. Okay? If you have to ask the server, then you did not, I mean, you could do that. That's not a bad approach, but it does not actually achieve some aspect of why you have caches, which is to reduce server load. Yes. You are saying if there's a cache miss, you only send it to the parent. Is that what you said? Okay, so you can figure out if it's existing in the children or not. So there are two approaches, right? This approach says, you have something to say? Yeah, you can put a bar. You can say, after I ask 4 caches, I'm just going to go to the server because it's taking too long. Okay, you can do that too, right? So all good ideas, but here is a approach that kind of does away with some of this overhead. So you see, first of all, those black nodes are caches. Okay, that square at the top is the server. Those white boxes at the bottom are clients. Okay, so it's no longer a hierarchy, right? It's basically a flat level where you have clients, proxies, and servers, but these proxy caches are still cooperating with one another. Okay? But there's one difference, which is every proxy now has a table, okay, that not only tracks what is in its cache, okay, that you have to keep track of, right? But it also keeps track of what is present in nearby caches. Okay? So you just have a table saying these are pages in my local cache. These are web pages in nearby cache 1. These are web pages in nearby cache 2. Okay? Now, a client sends a request to the cache. You do a table lookup. Okay? The table lookup says it's locally present, then you're done. You just fetch it from your local cache, send it. The table lookup says it's nearby cache 2 has it. You ask that cache, you get it from the cache, and you send it. The table lookup turns up empty. You say that's a global miss. Nobody seems to have it. So you just go to the server and fetch it. Right? So you basically removed all of that message exchange and replaced it with just a table lookup. And you solved the problem of having slow global misses, because now you are not asking a lot of caches before you figure out no cache in the system has the page before you go to the server. Is that clear, what I just said? Okay. So that's shown in this example here, where you have a table. This is a trivial example. You're trying to get the same web page A, okay? And here's that one entry in the table which says X has it. Okay? So the client is sending a read request for A. The local cache doesn't have it. It does a table lookup. The table lookup says X has it. So you see the red arrow goes to node X. You fetch X and you return it. Is that clear? Yes. Okay, question. That's a good question. Which was going to be my question also is, how is this table actually maintained? Okay? Because now every cache has to track not only its content but all the contents at nearby caches. And remember, caches are performing cache replacement. They're invalidating entries. So the contents in the cache keep changing. Okay, so the tables at all of the caches have to be kept up to date. The table is out of date. Okay, this idea is not going to work very well, right? For example, if the web page was nearby but you never updated the table, you'll go to the server. That's wasted extra overhead. Okay? Or vice versa, if you think X has A and you send the request there, but X has already replaced A, then you are going to effectively send that request there, and then it won't find the page. Right? So you have these problems. So you got to make sure that table so essentially the consistency of the table has to be maintained, just as you maintain consistency of the cache. Whenever any cache makes an update to its local contents, it has to broadcast that information to all nearby proxies so that they can update their tables. Okay? So long as you have an accurate snapshot of whatever is in all the nearby caches and you keep that in your table, then everything works well. Okay? But if you have incorrect information, things may not work well. So the worst case is when you actually have a table entry indicating that a web page is in a nearby cache, but that cache has just replaced that entry but hasn't yet updated the table. Okay? So you can assume now you ask for object A, the table says it's at X. X had A, but it just invalidated it, just removed it. But before it can send a message, say, to update the tables, this proxy is going to send a request there. Okay? It will arrive at X. X will say it doesn't have it, but then it will say it's a miss, so it will go to the server, get it, update the page, and send. Right? So the worst case is the lookups are always local. Okay? Hits are at most 2 hops, because either you get a local hit or you get a remote hit or another cache. But misses are also at most 2 hops. Right? So you can get a miss where the table says no one has it. You just go to the server, get it. But you can also make a mistake where you think somebody else has it, you send it there and they have just replaced it. Okay, then you have to basically have an extra hop, but that's okay. That will be rare, hopefully, if you have good table update protocols. Is that clear? Okay, so this is now doing cooperative caching, but it got rid of all of the hierarchical problems and slow global misses. You have a question? Yeah. Correct. So that brings us to the last part of what I want to say today, which is effectively gets us to content delivery networks and edge computing. So edge computing essentially is a field that is analogous to cloud computing, which now you have some familiarity with. You did a lablet, you're going to use it in the lab and so on. Okay? So what edge computing says is, rather than putting lots of resources in a large data center and calling it the cloud, let's put compute and storage resources at the edge of the network, which is close to the user. This is why it's called edge computing, right? So edge essentially means it's at the boundary of the network where the users are actually about to access it, right? So you, for example, if you have, let's say, a Wi-Fi router in your house, you have someone who's providing you Wi-Fi service. Okay, so if you deploy these resources one hop away, okay, that's the edge of the network, right? So that's fairly close to the user. Okay, so the idea in this case is, whenever you deploy these resources close to users, they are good from a latency perspective, because now the user can access this service, whatever that service is, at the edge instead of going to a remote server. Okay? Our web proxies already embodied that idea. We had implicitly assumed that our proxies are close to users. Otherwise, there would be no reason to do proxy caching. You may as well go to the server. The proxies are far away. So we have already assumed that the proxies are close. In effect, we were assuming that the proxies are deployed at the edge of the network. Okay? That way, when a user accesses a web page, you go to a fairly close by resource, which is your web proxy. Okay? Access it from there if it's a hit, and you're done. Right? Now, edge computing will generalize this idea, saying you don't just need to deploy caches at the edge. You can deploy any service. You can deploy web service. You can deploy other types of services from the edge. You can stream from the edge if you're watching a YouTube video, rather than it coming from a far-off server. If that video is cached nearby, you can actually stream from that. So there are lots of services you can implement if you have resources at the edge. And so there are many providers that specialize in edge computing, and there are also cloud computing providers which have started deploying resources at the edge. So if you actually go and look at, you have all now have Amazon credentials. If you go look at Amazon services, you will see it also offers edge services. Right? So you don't need to just get a server from US East or US Central, which actually gets your server either in Virginia or in Ohio. You can actually go to what's called an AWS local zone. There's a local zone in Boston, for example. So they have deployed servers there. So that's not really edge, but it's close to you, much closer than going to Ohio or Virginia. Right? So, but they're also deploying caches, which are even closer. Right? So you can use AWS servers to actually deploy your caching services and cache close to the users and so on. Okay? So this has now become an entire area of research and also for industry to provide services at low latency. Right? So we'll talk about all kinds of things you can do, but the thing you want to keep in mind is lower latency than edge cloud servers, because edge servers are closer to users. Potentially higher bandwidth, because you don't have to go multiple hops on the internet where some routers may be congested and you might get worse network bandwidth. So you might get higher bandwidth from the edge, and you can tolerate failures in the core of the network, because the edge might still be connected to you, but there might be faults elsewhere. So you can actually be a little more resilient to network failures than if you are actually accessing cloud. So this entire area actually complements cloud computing in many different ways. Okay? So in some cases, you might choose to deploy your services on the cloud. In other cases, you might have decided to do it on the edge. In some cases, it may be a combination. Web proxy caching said the servers are in the cloud, the web servers, but the proxies are at the edge. Right? So you're deploying now resources at both locations. Okay? So a little bit of history before we start talking about details. This whole area actually arose from two different domains. Okay? So there were two things that were happening in the late 90s, early 2000, both of which actually gave rise to what is called edge computing today. So the first thing is content delivery networks, and the second thing is mobile computing. So let me give you a little history about both, then we'll talk about the details. So content delivery networks are essentially, think of them as commercial services or companies that are in the business of providing caching as a service. Right? So if you need to deploy web caching for your website, rather than deploying your own web caches, you just go to a CDN, which has already deployed these caches at lots and lots of locations, and you just sign a contract and say, cache my web pages and deliver them. And then the CDN service will start caching your pages, and users will be directed to nearby caches rather than the server. So CDNs are essentially companies or commercial services that have deployed a very large number of caches already for you. So anyone who has a website or maybe has a website with a lot of rich content, okay, can just sign up for caching service and offload the content to cache and deploy it. I mean, not deploy, deliver it from the cache. Okay? So this is especially useful if your web page has lots of images and video, because delivering that content from the server increases the load on the server. But if you put these items in the cache, then users can access them from the cache. The load on the server is reduced. You don't need a big server. You can have a small server with a big CDN sitting in front of it, and it will absorb the workload for you. Right? So that's one area that gave rise to edge computing. So it started with caching, but then CDN provider said, we already have these servers. Why not do other things? Why not also host applications? We can put some containers on the cache and then deploy other services. So that gave rise to edge computing. Okay? That's one area. The other area that gave rise to this notion of edge was mobile computing. Okay? So back in the 90s and early 2000s, you had laptops and maybe other mobile devices. There were no smartphones back then, okay, that were still fairly limited in their capabilities. Okay? Limited amount of processing, limited battery power, maybe 1-2 hour battery life, not a lot of storage, and so on. So if you wanted to run any compute intensive application on your laptop, either it would run very slow, or it would basically chew up your battery and you would be out of battery very quickly. Okay? So one thing you could do as a mobile computing application developer was to not necessarily run the application locally, but run it on a nearby server and then have it send results back to you. Okay? So this was called computational offloading. Right? So computational offload basically says you can take any application or part of an application and then just run that part on a nearby server, which in this case happened to be an edge server, and then have it do all the work for you. And this edge server was maybe a server that does not battery powered. It's using grid power, so it doesn't have the same problems. It's a standard server, so it is more capable than a mobile device. So you could essentially do all of that extra work on a nearby server. Okay? So that's computational offload. And because the server was nearby, you can do low latency offload. Okay? Now, today's laptops are a lot more powerful, but that problem hasn't gone away. There are other mobile devices that have the same problem. Right? So take AR, VR headsets as an example. Right? So you can wear those headsets. They have limited amount of battery on them. They're doing lots of compute because they're showing you high resolution content, but they don't have the resources. They don't have a GPU on them or anything like that. Okay? So often these AR, VR headsets depend on a nearby PC or a nearby server that's doing all the compute and just sending it content to display. Right? So your application doesn't actually run on the headset. It runs on an edge server or maybe a local PC and is displaying it. Right? So that's an example of using edge computing for new generations of devices. But in the old days, you didn't have powerful mobile devices, so every device that needed to run more compute-intensive workload used edge offload. Right? So that's our history. Okay? So this has come from two different domains. But with that history, let's talk a little bit about some details of CDNs. Okay? So here is the use case of a CDN. I'm going to talk about one commercial one, which is called Akamai. Okay? So this was the earliest deployer of CDN. It's still the biggest one today. Okay? So they have hundreds of thousands of servers that are deployed in more than 1,000 networks in, I mean, across maybe 80 or more countries now. Right? So practically anywhere you go, okay, there is going to be a Akamai cache nearby. Okay? There are several of these Akamai caches in the UMass network, for example. So if you have any website that has signed up for CDN service from Akamai, access that website, your content is actually coming from a machine that's at UMass. Even though you might think you're actually accessing some other website far away, the content is cached locally. So you get it fairly quickly. Right? So only for services that use these CDN providers. Right? So practically every news website, streaming websites, they all use this type of content. Like Netflix, for example, runs on a very large CDN. YouTube has its own big CDN that's used to deliver content. So video services make heavy use of CDN services. That way, you can deliver this content from nearby caches rather than from a distant server. But lots of web content does that too. Okay? Now, the way this is going to work, okay, you might say, okay, let's say I go to CNN or New York Times website. Okay? When I put that URL in my browser is actually connecting to that server. Right? How is the content coming from the cache? How does this work? Right? So I'll give you an example of how you can actually make this work, and then we will come back to the slides here. So here is a client. Okay? The client is trying to access some content. Okay? So here is the origin server. So let's say assume that's the CNN server, that's a web browser. Okay? So the first web page has to come from the origin server. So maybe you go www.cnn.com index.html. Okay? That web page you will get from the server. Okay? And that's going to come back to the client. But inside that web page will be embedded all kinds of images or video content or whatever else you have on that web page. Okay? So all of those links, okay, will now actually point to a cache URL rather than the CNN URL. Okay? So essentially, maybe rather than saying cnn.com/image.jpg, you will basically have akamai.cnn.com or something like that /image.ca. So when the client tries to get it, it will now go to a cache and fetch it rather than going to the server, because you have replaced the links inside a web page with CDN versions of those links. So the links are pointing to cache rather than pointing to server. Is that clear? Okay. So that's the first thing. Okay. But that's not all of it. Okay. Because what I told you that this CDN service might have hundreds of thousands of caches. Okay. So you just pointed it to a generic cache. How is it going to come from a specific one? Right? So this is where some of the intelligence comes in. The client is going to try to resolve that URL to an IP address. Right? So it's going to do what's called a DNS lookup. DNS stands for the domain name system. Okay? DNS is the service on the internet that takes a name of a machine and gives you its IP address. So if you say www.umass.edu, your web browser actually sends that to a DNS server. The DNS server will give you the IP address. Okay? And then if you have the IP address, then you can connect. Right? So you probably know what IP address and port numbers are from your socket program. Right? So you are going to send that request to a DNS system. Okay? And then the DNS system, in this case, has intelligence. It figures out where is the client coming from. It does what is called geo IP location. It says the client is based in Amherst, Massachusetts. Right? So then it will ask, where is the nearest cache that I have that's close to this user? Okay? And then it will return the IP address of the nearest cache. Okay? So different users who are trying to get that exact same URL will get sent to different IP addresses that belong to different caches in the net. And that will be an IP address of a nearby cache. Right? So when you do this DNS resolution, this client will be sent to a nearby cache, and then that cache will return the results to. Right? So, and you will change where you send a user to based on their physical location and what is the closest cache that has the content. Right? So all of the hard work is actually being done in the DNS system, which is doing redirection and load balancing. And we'll talk more about this next time because we ran out of time today. But that's the basic idea. of how a CDN works. Okay, so let's stop here. We'll continue tomorrow.